Welcome back to Calculus 2, Section 5.2, Infinite Series. So we have a number of topics to go over. We're going to start by defining a series. We're going to look at a few types of series, and along the way talk about properties of convergent series. Let's get started. So here is the definition. We want to start with a sequence of an infinite number of terms. Then the series is simply the sum of all of those terms. We have different ways to represent that. We can represent it as start with the first, add in the second, add in the third, and so forth. Or equivalently, we can use summation notation to say add up from the very first term through all of the terms, each term of the sequence. All right. Now, the big consideration is whether or not the infinite series represents a value. Another way to state that is whether or not it will converge. Our tool for studying the convergence of series are partial sums. So instead of trying to add in one go all infinite number of terms from the sequence, we can add just the first few terms of the sequence. We'll call that a kth partial sum. Add the first with the second with the third until you get out to the kth term. This then gives you a sequence of partial sums, and we'll study the behavior of this sequence in order to determine the convergence or divergence of the overall series. So the kth partial sum is a nice tool for us. Thus, when we look at the convergence of the sequence of partial sums, if we suppose that the sequence converges to some value s, then we're able to say that the series is equal to that limit s. And we say of the series, we say that it converges. Likewise, if that does not happen, then the series, we say, diverges. All right, very good. Let's do an example. Now, we can start with a series which is a constant. Every term is a fixed constant. Take the constant 0. Well, you know that 0 is 0. Add in another 0, you still have 0. Add in yet another 0, and you still have 0. Thus, this sequence defines an infinite series that converges, and it converges to 0. On the other hand, if we use any constant other than 0, then the series that sequence defines will diverge. Just think of the sequence of terms, which are all 1. Add 1 to 1, you grow in value. Add another 1, you grow in value yet again. There's no hope of the sum of these terms to be finite valued. Very good. Okay, so here's an opportunity for you to play around a little bit. Suppose that the sequence ping-pongs back and forth between 1 and -1. Does this sequence determine a series which is convergent or divergent? Hint, it's divergent. Think of the reason why. Nice. All right. Let's take a rectangle. Let's suppose that the length of the rectangle is 2. The width of the rectangle is 1. The area enclosed by the rectangle is 2 square units. Now, divide the entirety of the enclosed region into 2 equal portions, then each portion will be of area 1. Pick one of those 2 and shade. Then the amount that you have shaded is 1 square unit. Term that A1. We're going to create a sequence of terms. Well, how are we going to do that? We're going to take whatever is remaining, the unshaded portion, divide it into 2, and shade one of the 2. Now, how much have we shaded? We've shaded a half of the first term, 1. So, how much are we going to shade next? Half of the 1/2, or a fourth. That's our third term. What's our fourth term going to be? Half of a quarter, or 1/8. Okay, so repeat this ad infinitum, and notice that as we repeat this process, the amount that we're taking half of gets smaller and smaller and smaller, and that if we repeat this process ad infinitum, that eventually we're going to exhaust the entire original area, and that each time we repeat the process, the amount that we're looking at adding in is infinitesimal, becomes infinitely small. All right, but if we add all these back up together and we look at, well, what did we originally start with? We know that we started with 2. How can we recover this 2? By taking each half that we took in our sequence, 1, and then a half, and then a fourth, and so forth, and add them all up together. And doing so recovers the original 2 square units. All right, so the summation on the left represents an infinite series, and the quantity on the right represents its limit. Alternate notation for this would be to say that we're taking the limit of the kth partial sums. Note the summand is 1 over 2 raised to the n minus 1. And that's just notation for 1 over 2 raised to a power, where the power begins at 0. And this is the idea of a convergent infinite series. When we use the word converge, built into that is the notion of taking a limit. This boxed statement can equivalently be written down as the infinite series is equal, put an equal sign, to 2. That means that the value that the infinite series represents is this quantity. Using the verbiage converges to speaks to the idea of a limiting process. And limiting processes are inherent, are fundamental to calculus. Nice. Your turn? Well, in this assignment, it looks like there's nothing to do. The 2 series are identical. Oh, wait a minute. There's a small difference. So investigate what this small difference has in the value represented by this infinite series. Okay. Right, so that's an overview, the definition of a series, and a few different notions of a limit and convergent divergent series. Let's look at our first instance of a particular series, the harmonic series. What does it look like? Here's what it looks like. So it's an infinite series. We're summing up an infinite number of terms. What do the terms look like? 1 over the index. This is what? This is the harmonic series. Let's write out the first few terms in the harmonic series. So the index begins at 1. So the very first term that we're going to write down is 1, 1 over 1. Next, 1 over 2, and so forth. Now, we want to consider the convergence / divergence of the series. Our tool is partial sums. Let's write down the first partial sum, S1. That's just the first term. Note that I'm going to use k for the index of the partial sum. So here's k equal 1, the first partial sum. Let's go to the next partial sum, S sub 2. And this S sub 2 has the value 3 over 2. I'm going to refrain from writing it out that way. I want to look at this as 1 and then add in a copy of 1/2 so that if I can go back and compare it with S1, I had 1 and add in 0 copies of 1/2. Now, in order to get 1 and then another copy of 1/2, I'm going to jump from k equal 3, I'm going to jump out to k equal 4. And that's going to allow me to look at the two terms that have been added in to produce from S2 to produce S4. The two terms, these guys here, 1/3 and 1/4. What do we know about 1/3? Well, one thing is that it's bigger than 1/4. Oh, and if you have a 4th and then another copy of a 4th, you would have exactly 1/2, so that this quantity is actually bigger than 1/2. And thus we're getting that we had 1, add in 1 copy of a 1/2, and now we're adding in something that is even bigger than 1/2, allowing us to make the statement that S4 is bigger than 1 plus 2 copies of 1/2. Okay, so let's back up and look where we were. So we had S1 is bigger than or equal to 1 plus 0 copies of a 1/2. S2 is bigger than or equal to 1 plus 1 copy of a 1/2. S4 is bigger than or equal 1 plus 2 copies of 1/2. And note the index of these partial sums expressed in base 2. You would have exponents 0, 0 copies of 1/2. Exponent 1, 1 copy of a 1/2. Exponent 2, 2 copies of a 1/2. So if we want to think about, well, when would we next have 1 plus 3 copies of a 1/2, we should use 3 as our exponent. In other words, S sub 8. So let's look at S sub 8, which is S sub 2 to the 3. S sub 8 is S sub 2 to the 3. And here are the sum of the first 8 terms in the harmonic series. We've already looked at S4. Then we're adding in 4 more terms in order to produce S sub 8. And if you look at the very last term, each of the preceding 3 terms are each bigger than 1/8. But then 4 copies of 1/8 would give you a 1/2. Therefore, the sum of these 4 terms are bigger than a 1/2. Thus, S sub 8 is bigger than or equal 1 plus 3 copies of 1/2. Where's the 3 coming from? That was the exponent on 2 in order to equal 8. So, looking out at indices 2 to the n, we know that the 2 to the nth partial sum will be bigger than or equal 1 plus n copies of 1/2. Well, what is the behavior of n times a 1/2 if we let n go to infinity? We know that that value will tend towards infinity. And then what's true about the partial sum? It's bigger than this quantity. Thus, this value is tending towards infinity, which is to say that the harmonic series diverges. So you want to make note of this. You want to imprint this strongly into your brain, that the harmonic series diverges. That the harmonic series is of the form 1 over the index. All right, very nice. So here is a divergent series. Okay, so 3 different infinite series where you want to investigate the convergence or divergence by looking at partial sums. If you get stuck, please open up the book and you should find some help there. Nice. So we've had the definition and we've looked at a particular series, the harmonic series. Harmonic series will be a key example for us. Now, we'll look at some properties on convergent series. Let's get started on that. So suppose that we have 2 different series. One of the series is given by a sequence labeled ANs, and the second given by a series BNs. We want to assume that each of these infinite series represents a finite value. In other words, each is convergent. For simplicity, you can think in your head that the first represents capital A and the second represents capital B. All right. If we were to take the sequence of ANs and the sequence of BNs and add corresponding terms, AN plus BN, we would produce a new third sequence. And that sequence determines a series. Well, if we're taking terms AN and BN and summing them from convergent series, then we might assume that we're going to produce a convergent series, and in fact we do. Moreover, this convergent series, what value does it converge to? It converges to the sum of the values represented by the 2 convergent series. So what you would naturally hope or expect to happen, here we're stating that it does indeed hold. It does indeed happen. Okay, so that's the first property. And the second property is nearly identical. We're just going to swap out the sum for a difference. Now, if you're thinking, well, these are obvious, fair play. However, note that we're dealing with infinity. And one of the objectives in this chapter 5 is to come to the appreciation that infinity is something rather different, that strange things can happen at infinity. Right? Hence, we use limits when we're dealing with infinity. And approaching infinity with care requires that these types of statements are necessary. Now, somewhere else where we've had summation and limits applied to summation is in writing down definite integrals. Think about the Riemann sum. And very much so, if you were to replace out these infinite summations with integrals, and then think back to properties on integrals, then these statements look very much like properties of integrals. What's another property of integral that we can mimic? It would be that we can pull constants through the operation of integration. Likewise, if we have an infinite series which converges, then introducing a constant onto each term in the associated sequence, producing a new sequence, well, we can actually pull that constant out to the front. Very nice. Okay, so your turn to play around with these three properties. Assume that the value for capital A is 2, the value for capital B is 1. Note well that you're also provided with the value of the very first term, A1, and the value of the very first term, B1. Good. So that piece of information, A1 and B1, are relevant in analyzing number 3. Excellent. So we've had the definition. We've looked at the harmonic series, summation of 1 over n, and 3 different properties for convergent series. In the previous video, section 5.1 on sequences, we had 2 salient sequences. The arithmetic sequence adding in a constant, and the geometric multiplying by a constant. Let's go back and think of what that geometric sequence was. The nth term can be expressed as the very first term multiplied by the common ratio r, n minus 1 times. So this defines a sequence. What type of sequence? A sequence called the geometric sequence. If we want to write down the geometric series, we need a geometric sequence. And then the series would be add up all those terms. Very good. Write out the kth partial sum. And then we're going to use this kth partial sum in order to determine, to find, investigate when does the geometric series converge. Okay, so we need this S sub k. Note that the very first term in a partial sum is a quantity A. To move to the next term, you multiply by r. And then moving to the next term, you multiply by r again. So we have the first term, the second term, the third term, and then this is the kth term. Thus, we're looking at S sub k. All right. A convenient trick is to now multiply S sub k by r, and then present in this line is a sub r, is a times r squared, is a times r cubed, which is matching term by term with the first line, everything except for the a. And in the second line, all of the terms match except for the very last term, a times r to the k. Oh, well, if we have representation in the second line as well as the first line, and we take the difference of these two quantities, we produce lots and lots of cancellation. So take the top row minus the second row, top row minus the second row, and everything cancels out except for the very first term in the top row and the very last term in the bottom row. So after everything cancels out, we're left with just the first term from the first row and the very last term from the second row. Good. Let's work with this equation. On the left and on the right, let's factor off the common factor. And then the quantity that we're interested in is the partial sum, S sub k. So divide through by 1 minus r. And then we have an expression for the kth partial sum of a geometric series. And the point of looking at this kth partial sum, finding an expression for it, is to aid us in studying the convergence of a geometric series. Well, if we want to know about convergence, that means that we're going to watch what happens as we let k get large. But letting k get large has no effect on the constant a, has no effect on the constant r. Letting k get large only affects this term, r raised to the k. So we want r to the k to converge. We want it to converge to a constant. Now, if we let r equal 1, we have problems because the denominator is not defined. I'll leave it to you to think about the case if r is -1, why that's a bad situation. But otherwise, we can think of r taken strictly between -1 and 1. And when r is strictly between -1 and 1, small times itself is even smaller. And if you repeat that smaller and smaller and smaller, what do you get? You get that this term will tend towards 0 anytime r is taken between -1 and 1. So if this term as k goes out to infinity, if this term tends to 0, we can simply scratch it off and write down what we're left with. Constant a times 1 is just a, and the denominator is the denominator. Now, I talked briefly about r equaling 1 and briefly about r equaling -1. All other cases, if little r is bigger than 1 in absolute, then this r to the k will tend to positive infinity or negative infinity or ping pong back and forth between extremely large, positive, negative. All right, so this is the analysis of the geometric series where there are conditions on the common ratio r in whether or not the series converges. In most cases, it will diverge. In order to come up with a convergent geometric series, we need the common ratio to be small. What does that mean? In absolute value, it must be strictly less than 1. Okay, so to the harmonic series, we've now added in the geometric series. Let's play around with it. Okay. So here we have a series. We're starting with the first term of +1. Moving to the second term, if we multiply by 1, we get the second term. Excuse me, if we multiply by e over pi, we get the second term. Multiply the second term by e over pi, and we get the third term. Third term multiplied by e over pi, we get the fourth term, and so forth. Thus, we're looking at a geometric series. Well, does it converge? What was the condition? We need to look at the common ratio. So moving from term to term, what are you doing? You're multiplying by the common ratio. What is the common ratio? E over pi. What can you say about e over pi? It's a quotient with the numerator smaller than the denominator. Thus, what's true about the quotient? That quotient r, e over pi, that quotient r, e over pi, is of size strictly less than 1. This numerator is smaller than that denominator. So, what do we get? We get that this converges, the geometric series converges. What's the formula? You take the very first term, quotient that with 1 minus the common ratio. What is the very first term? 1. So we get a numerator 1. What's the denominator? 1 minus the common ratio. 1 minus e over pi. Nice. So this geometric series converges. And we can actually find the limit it converges to. Nice. All right, in this assignment, you have 2 different geometric series. You want to investigate whether it converges or diverges. In the case that this series converges, go ahead and write down the actual value. The presentation of the geometric series are given in two different forms. One, the first one, similar to the example that we worked, and the second one telling you the very first term and a ratio of the current term over the next term. Right? Nice. So the two series that we've seen so far are the harmonic, 1 over n. What happens with the harmonic? Does it converge or diverge? Make sure that you have that down. And the geometric, what's the condition on a geometric series converging? Make sure you have that clear in your head. Here's another type of series called the telescoping series. We're going to see that we're going to get terms canceling to lead to convergence in some situations. Let's take a look at this example. We have an infinite series. Note that the index here is beginning at 2. The associated sequence is given in terms of a natural log. And we're taking log of a sum of two terms. Let's apply algebra and rewrite the 1 as n over n in order to combine these two terms as a single term. All right, so when we look at the series, well, what can we do? You're investigating. Hey, maybe we can use algebra. See if anything pops out. Oh, wait, now we're taking the natural log of a quotient, and we have a quotient rule for the natural logs. So that log of the quotient becomes a difference of logs. This is interesting. Note that the difference is saying that we're going to add a quantity in, but then we're immediately going to take a quantity away. We're adding in a quantity and then taking away, and these two quantities, if you observe the graph of the natural log, these two quantities are rather close to each other in value. Well, if the difference of two quantities which are close to each other is going to be a small quantity, and if you think back to that rectangle that we started with of area 2, that the further out we went in our sequence, the smaller and smaller the terms are. So in order to have a convergent series, we want to be adding in smaller and smaller terms. So this looks promising as these two quantities, ln of n plus 1 and ln of n, should get nice and close to each other so that as we go further out in the associated sequence, the terms get smaller and smaller. All right, so that's a general idea on convergence. This notion of telescoping series is going to look more explicitly at how terms cancel out. So let's put on a different pair of glasses now and investigate telescoping series. And the way that we're going to investigate telescoping series is to write down partial sums. So the first partial sum is the first, starting with the index n equal 2, just plug in. 2 plus 1 gives us 3, and n is 2. So this is the first partial sum. Move on. We're looking for a pattern. Move on. S sub 2. Well, it's going to be the n equal 2 term as well as the n equal 3 term. And what you can do is you can just look at the arguments to the natural logs and bump them up by 1. But as you do that, you should note here that the ln of 3 will cancel with ln of 3, leaving a positive ln of 4 and a negative ln of 2. So write that down. Pause for a second and go back and look. What was S1? ln of 3 minus ln of 2. Now what do we have? ln of 4 minus the same ln of 2. All right, so the ln of 2 is repeating. Let's look at S3. And S3 will be S2, so here's S2. And then add in the next term, which corresponds with n equal 4. So 4 plus 1 is 5, and n is equal to 4. Compare. We get another cancellation. ln of 4's go away, leaving us with S3 being ln of 5 minus ln of 2. Now you can see a pattern, ln of 3 minus a constant, ln of 4 minus a constant, ln of 5 minus a constant, so that the partial sum, S sub k, will be ln of that index k plus 2 minus the constant 2. ln of 2 is a constant, but ln of k plus 2 will tend to infinity. Thus, S sub k will tend to infinity. All right, so despite the fact that these two quantities are going to be close to each other, they're not coming together fast enough, and this infinite series will diverge, since the partial sums are tending towards infinity. Nice. So this is the notion of a telescoping series, where you're looking at cancellations occurring. And then thanks to those cancellations, you're able to come up with a form of the kth partial sum, and then observe, does that kth partial sum as a sequence converge or diverge? So the second example that you have here is in a way reusing the work that we did. So use algebra in the numerator. On the first one, this, again, you want to think back to the notion of integration, and partial fractions was a method for integrating. Use partial fractions to break up this expression. And then you'll have either a sum or difference, and you can investigate that. Very nice. That brings us to the end of this video. Thank you so much for watching. Please like if you find the video useful, and I will see you on the next one.